Welcome to this explainer. Okay, I want you to do me a favor. Just take a look at the device you're watching this on right now. Or, look down at the shoes you're wearing. Chances are they spent weeks on a ship to get to you. Today, we're diving into a massive industrial pivot happening right now in the global shipping industry, which is basically the mechanical backbone of international trade. And what's absolutely wild here is how this heavy industry is literally raiding its own past to try and hit a net zero emissions target by the year 2050. It's this incredible story blending physics, insane engineering, and a real race against the clock. Let's get into it.
So we've got to start right here. Are sails actually making a comeback? It's kind of a brilliant irony, right? I mean, for centuries, wind was literally the only way to move across the oceans. That is, until diesel engines came along and made everything, well, faster, much heavier, and a whole lot dirtier. But now, the modern titans of the sea, these massive freighters and container ships, are turning their attention right back to the wind. But as you're about to see, these are absolutely not the sails of the past. Okay, let's dive into this roadmap. First, we'll look at the return of wind power overall. Then, we're breaking down three specific, honestly mind-blowing technologies: aerofoils, rotors using something called the Magnus effect, and finally, kite sails. To wrap it all up, we'll check out the future fuels required to actually hit that net zero goal. Section 1. The return of wind power, moving beyond the Romantic era. Look, when we hear the word sail, our minds naturally go straight to the Romantic era of tall ships. Wooden masts, lots of rigging, miles of canvas catching a tailwind. But today's urgent push for sustainability means the industry can't rely on romance. They desperately need wind-assisted, high-tech systems that can integrate seamlessly with modern logistics to reliably move thousands of tons of cargo. Moving to Section 2, aerofoils, or vertical airplane wings. Seriously, if you're picturing billowing sheets of fabric right now, just throw that image completely out the window. The cutting edge of wind propulsion today looks way more like aerospace engineering than traditional maritime rigging. Now, what's really interesting about the physics here is the stark contrast. On one side, traditional sails are essentially giant sheets of material that literally just catch the wind to push a vessel forward. They work best when the wind is blowing straight from behind. But modern aerofoils, they are contoured on one side and flat on the other, literally exactly like an airplane wing, just standing vertically. As air moves faster across that contoured surface, it actually reduces the air pressure. This creates a sort of lift that translates directly into forward thrust. It pulls the boat along. And because of that weird quirk of physics, their optimal wind direction is actually from the side to maximize the surface area hitting the breeze.
And we really have to pause for a second to just appreciate the sheer scale of these modern structures. 80 meters. Some of these telescopic wings can tower 80 meters above the deck. That's like stacking a 20-story building on top of a ship. And because they're telescopic, they can cleverly retract and lower right down to the deck. This is crucial because it allows these massive ships to safely pass under bridges or squeeze into tight, restricted harbors. They even rotate on their axis automatically to catch the absolute perfect angle of the wind.
So, you might be wondering, why go through all this crazy engineering trouble? Well, check out this number, 90%. That is the staggering reduction in carbon footprint that a modern wing-powered design like the Oceanbird concept is aiming for. Now, sure, there is a trade-off here. This type of vessel is designed to be slower. It might take about 12 days to cross the Atlantic, compared to the 6 days it takes a standard dirty diesel vessel. But for a 90% drop in emissions and massive fuel savings, a lot of folks in the industry believe that trade-off is absolutely worth making.
Okay, Section 3, rotors and the Magnus effect. If aerofoils look like airplane wings, this next technology looks less like a sail and honestly way more like a giant spinning industrial smokestack bolted right onto the deck. The secret sauce of this tech relies on something called the Magnus effect. It was named after a German inventor, Anton Flettner, who actually came up with this idea way back in the 1920s. The system uses these massive rotating cylinders called Flettner rotors, and freight operators absolutely love this technology today because it's just so practical. These giant spinning cylinders can often be retrofitted onto the deck of a ship that's already in service in just a single day. It's a huge, immediate, quick win for efficiency. Let's move along and see how this builds, step by step. Step 1, rotation and airflow. As these massive vertical cylinders spin on the deck, they mess with the passing wind, causing air to move faster across one side of the cylinder and slower across the opposite side. Step 2, pressure differential. Just like we saw with the aerofoil, this difference in airspeed means the side with the faster moving air experiences lower air pressure. And finally, step 3, forward thrust. That pressure imbalance literally causes the cylinder and the massive ship it's attached to get sucked toward that lower pressure area. It effectively just shoves the boat along the water. To really cement this in your mind, just think about sports. Think about how athletes in baseball or cricket or soccer put spin on a ball to bend its trajectory midair. That wicked curveball in baseball or that bending free kick in soccer, that is the Magnus effect in action. In shipping, instead of curving a little ball, they are harnessing that exact same spinning force to help propel thousands of tons of freight across the ocean, which takes a massive workload off the ship's traditional engines. Moving on to Section 4, kite sails and high-altitude winds. Now, I have to warn you, if the rotating deck cylinders seemed a bit unusual, this is where the designs start to look truly wacky to the layman's eye. But I promise you, the science behind it is fiercely logical. 300. We're talking about 300 meters above the sea. Instead of mounting a giant structure directly onto the deck, these systems use a massive kite tethered to the ship by a long rope, deployed and controlled by a winch system. Why on earth would you fly a kite that high? Well, because at 300 meters up, the wind encounters far less friction from the water's surface. So the winds up there are significantly stronger and much more consistent than the breezes you'd feel standing down at deck level. So the crucial point is understanding the balance of pros and cons here. The benefits are massive. Accessing those strong, high-altitude winds can lead to an estimated 10 to 35% reduction in fuel consumption for large ships. Even better, because the kite flies way up on a winch, it completely preserves all that incredibly valuable deck space below. Container ships can be fully loaded without a giant rotor or wing getting in the way of the cargo boxes. Plus, they're super easy to retrofit. On the flip side, though, these are strictly complementary systems. They assist the engine. They definitely don't replace it entirely. They also face a bit of an image problem, looking a bit, well, bonkers to traditional ship operators. And compared to other methods, there's still fairly limited long-term operational data across the global fleet. But this isn't just theory drawn on a whiteboard. During actual tests, a 160 square meter kite sail on a ship called the MS Beluga Sky Sails managed to save around 2.5 tons of fuel every single day. That equated to a direct financial savings of 1,000 books a day. When you scale that up over months and months at sea, you can see exactly why operators are so eager to figure this out and harness the tech. Section 5, Future Fuels and Net Zero. This is the ultimate goal. We've talked a lot about wind so far, but it's absolutely vital to remember that all these incredible sails, rotors, and kites are ultimately just assist technologies. If the industry is going to reach absolute net zero by 2050, the primary mechanical engines of these ships still need a massive, clean overhaul. Let's take an impartial look at the chemical fuel replacements for standard diesel. There is a very clear dividing line here based on the type of voyage. For long-distance, transoceanic routes, where you absolutely need incredibly high energy density to cross entire oceans without stopping, the leading zero and low-carbon candidates are biofuels, hydrogen, and ammonia. In contrast, while battery technology is fantastic and advancing rapidly, the sheer weight and energy limitations mean batteries are currently slated primarily for short-distance, coastal voyages, and ferries. And this really brings us to the grand compromise the entire industry is grappling with right now. We have the 12-day crossing versus the 6-day crossing. On one side, you've got the future, wind-assisted, utilizing new alternative fuels, incredibly low carbon, highly efficient, but undeniably slower. On the other side, you have our present reality, traditional diesel engines that are super fast and reliable, but high in carbon emissions and totally environmentally unsustainable in the long run.
So what does all this mean for us? It leaves us with this final provocative thought to wrap up our explainer today. Are you ready for a slower, but much greener future of global shipping? If we truly want our goods shipped across the world with a net zero footprint by 2050, we might just have to accept that it's going to take a few extra days for that online package to arrive on our doorstep. It's a fascinating trade-off between the breakneck speed of the modern world and the sustainability of our planet's future. Thank you so much for joining me to explore this incredible journey. Keep questioning, keep learning, and I really hope this deep dive leaves you hungry to discover even more about the wild technologies shaping our world.